Happy to see you all. Thanks for coming. Great to see you and get to visit with you. And I look forward to answering your questions and helping in any way we can. Um, I am going to talk about some basic things. We'll get to that in a minute. I'm going to talk about partly some basic things. Some of the things, no doubt, be reviewed for most of you. This is meant to set a common ground for all this, and as Nikhil said, to talk about some methods of empirical interpreting data which are widely useful in structural estimation. Okay, so we're going to do that. There's also some things along the way. I didn't want those for whom this is all familiar to be completely bored. So we're going to do some new things along the way, which are also useful for structural estimation, including inequality restrictions. I'll talk a little bit about inference of inequality restriction. Okay, so along the way in the slides, I have places for a break, where I'll try and stop and you can ask questions. If you have questions in the middle, that's fine, raise your hand. Fedor is watching Tulip and online, and so if there are questions online, we'll be happy to take those too. Okay, so it's been a few weeks, so maybe a little bit rusty. I'm actually going to try and use the iPad and the program to highlight things. Okay, so that's a good thing. The menu comes up. All right, and so we're going to talk about some things. Okay, so all right, so firstly, so just as an outline, I'm going to describe maximum likelihood estimation. Sure. Do you mind if what? Sorry.
I just need to check. So you
Oh, yeah.
then we should be able to.
Sure. Yeah, whatever. Okay, so this program I'm working with allows me to highlight things. Okay, so we're going to briefly describe maximum likelihood estimation, GMM, give a really few examples and compare them a little bit. Again, this is just establishing some common ground. And then we'll talk about inference methods. And we're going to talk about the bootstrap a little bit and a particular variety of it, which has some very nice features when it's computationally feasible. And then want to also talk a little bit about how to test and impose and do inference with inequality restrictions. Those are important in structural estimation and lots of places in economics. And then we'll describe simulated moments estimation and to consider a set of examples from discrete choice. So I'm not going to ask for a show of hands on maximum likelihood, okay? But how about GMM? Is everybody familiar with GMM? Want to raise your hand if you're familiar with GMM? Oh, that's good. Okay. How about method of simulated moments? Okay, not everybody, but quite a few. Okay, that's okay. That's good. It's important to cover that. And so that'll be good. And we welcome your input and comments on that. And then the rest of it, how about I say discrete choice models? People, okay, so even more than the simulated moments. Okay, that's helpful. We're going to focus on a few discrete choice moments, discrete choice models in particular. Okay, so we'll get to that. All right. So these are some references that are useful. One, is the handbook chapter with Adam and I, which talks about maximum likelihood and GMM and lots of other things. Bootstrapping for inference. with inequality restrictions, that's just a pretty new paper. Well, it's actually from 2015. It should be available on the Econometrica website at this point. Method of simulated moments, there's some good references. These are kind of the fundamental papers. There's lots of other things written since then. The fundamental papers are Ariel Pecos. There's a paper on patents as options, which first paper I know of that really use simulation in this way to estimate a structural model, actually. So he did that in a brown bag lunch organized by Dan McFadden in about 1982. So a long time ago, and kind of, I think John Russ was in that same brown bag lunch that we had, and I think we saw dynamic discrete choice even in that. So that was amazing. This was a wonderful pioneering paper. And then, of course, McFadden's paper, Method of Simulated Moments, and Pecos and Pollard, the asymptotics for optimization estimators. Then discrete choice models, there's some notes. Alberto Abadi, my colleague here, has graciously agreed to share these notes. And so they'll be posted. These are notes from the second year econometrics course here. And they're quite comprehensive and good and clear. So they'll be available. I'll use a little selection from that. And then here's some other, these are all sort of fundamental, not sort of, these are fundamental papers on discrete choice. So I'll go through them all. Okay. Any questions? Anything? Okay. All right. So let's just start. So we're going to focus here on data. When you see a W in these notes, that's the whole data vector. And it consists of IID observations on possibly a large vector where that notation allows for clustering. Okay, so this is like in panel data, W would be the vector of observations over all time periods. And then we're going to assume that we're independently and identically distributed across individuals. Okay, this notation, it allows for clustering. So I'll try my hand at this. Allows for clustering, right? Allows for clustering. Okay, so that just means that within W, you can kind of have any dependence at all that you want. So it's panel data, any kind of dependence you want over time, but across individuals, we work with IID data. Independence of observations across eyes assumed throughout, imposed throughout. And then, the notation for the effect we're interested in, whatever it is. And actually all of the parameters you have to estimate to get it is theta naught. Okay, so that'll be the true parameter value of interest, p by 1 vector. So that includes whatever you're interested in and all the nuisance parameters as well, and what we're going to do. Okay, so what we'll do for just a few minutes is describe and compare maximum likelihood, GMM, method of simulated moments, and give some examples, and then how to explain how to do inference using the bootstrap with inequality restrictions. And then I just folded in the discrete choice into this. So this is going to cover both these notes cover both the first lecture and the second one. Okay, I just put it all in one document. Okay. Let's see. That cancels it. Okay, I'll save it next time. Okay, so further notation, the estimator is going to be theta hat, and that just denotes all it is a function of all the data. It's a guess about what the true parameter value is. It's a function of all the data. We generally suppress this notation, right? We don't write it like this. We're just going to write it like that. This theta hat. Okay. And then the maximum likelihood is based on the assumption that we know the form of the PDF, probability density function, of a data observation W up to some vector of parameters. Okay, so this includes discrete data where, f of W given theta would be a probability. No difference, nothing changes. Well, no need to get into why or what the underlying, measure theory is or anything. So anyway, nothing changes. Okay, so the maximum likelihood estimator, of course, as you know, it maximizes the probability density function of all of the data. And so you plug in the data, and then you pick the value of the parameter that maximizes the probability density function for the data that you have. Okay, so it's going to look at, so that's the density of all the data. Since it's IID, it's just the product of densities, evaluated it at the ith observation, and then you maximize that over all values of theta in some set of possible parameter values. Okay. Defined to me, it's the same thing when WI is discrete, and this is a probability instead of a density. And then, as usual, just a few little, the usual kind of simple algebra just to start us all off. Since monotonic transformation has the same maximizing value, you take natural log, divide by sample size n, and that gives the MLE as the maximizing value. That's what the argmax means. The notation means of the good density of the data. At some theta, you maximize that over theta, you multiply by 1 over n, take log, get the same thing. That's that. And then it's convenient for lots of reasons to think about this as 1 over n times the sum of the log likelihood for each observation. Okay, so that's of course the log likelihood with the log in there. Okay, so that's standard notation. Okay, so here the fundamental condition. Now I'm gonna just one condition for MLE is for it to be consistent and asymptotically normal, and then with some other conditions thrown in later we won't talk about. Focus on the one condition is this, that the density function of the data is actually f of w given theta naught for some theta naught. Okay, and that's what we call correct specification. In other words, you've really got the density right up to vector parameters. Okay, so that's important and essential for the MLE to work in most settings. And then the other condition that's really essential is identification. I think no one in this room would argue about that, but there's been kind of a funny thing going on among some areas of applied econometrics about this. Okay, and just here, identification is fundamental. Okay, and the condition for maximum likelihood is actually the identification condition, which says that if the parameter value, the vector is not equal to the true parameter, the density is different. So that's what identification means actually that's what it means, period, for identifying theta in this model, this likelihood model. Okay, and that's what allows you to distinguish the true value from other possible values of theta naught. And without that, you can't figure out what theta naught is. Okay. So now under this condition, under regularity conditions, standard properties that you know and love, particularly in structural estimation, are where you use we use maximum likelihood all the time, are these. Okay, so it's a little notation. J is the information matrix, which you can think of as just the second derivative of the log likelihood. So the Hessian matrix of the log likelihood evaluated at the true parameter. Take the negative of that and take its expectation. Okay, that's the information matrix, J hat. There's actually multiple ways to estimate this information matrix. We'll just write the one here that's largely thought to be the best in terms of its properties for standard errors and things. Okay, so you take the second derivative of the log likelihood in the data, and then the average log likelihood in the data, and then evaluate that at the MLE. Okay, so V, we'll define that to be the inverse of the information matrix, and V hat to be the inverse of the estimated information matrix. And then with assumption MLE, identification and correct specification, then and some other conditions, you get maximum likelihood of being asymptotically normal. Okay, so that's the asymptotic normality part and consistent estimation of the asymptotic variance. Okay, and all the way along, when you do inference, those are the two things you need. We'll mention that again. Okay. Right, so there's that proposition again. Okay, and we sometimes summarize the first two conditions as first two conclusions as under correct specification, identification, and other regularity conditions. MLE is consistent and asymptotically normal, CAN if you want, and with asymptotic variance V, and J hat's a consistent estimate of the asymptotic variance. So doing econometrics, that's what you're always shooting for when you prove a theorem about an estimator. What you want in the end, asymptotic normality, that's good, it's approximately normal. And then the other thing you want is a consistent estimator of the asymptotic variance. And why? So you can do inference of it. Okay, so that's two properties, right, of the MLE that are important. It's also true that it's efficient, okay, and MLE is efficient. In other words, if that model is really true that you have for the density, then maximum likelihood estimator has the smallest asymptotic variance in the positive semi-definite sense. Okay. Okay, so now often in applications, actually, we're not working with the full likelihood of the data, something that describes the distribution of every variable. We're actually working with a conditional likelihood. And in that conditional likelihood, the thing you're conditioning on is regressors. And you do that because nobody knows, nobody wants to impose distributional assumption for regressors. So oftentimes, actually, the likelihood function for a single observation is actually a conditional likelihood. And all we want to say about that is everything we just said is the same. Okay. You want to think about correct specification is important, that the distribution of y given x is correct, and that that suffices to identify the parameter. And the same definition of identification, changing theta changes the value of the conditional likelihood. Okay, and the same properties hold for conditional MLE. Okay. All right, okay, so this is one place I stop. Any questions, comments, suggestions, thoughts?
Maybe I'll break the ice. So often we concerned about our model being somewhat misspecified. And there is, can you say a little bit about the interpretation of MLE and how you recommend changing your inference procedure if that happens?
Yeah, so that's a great question. So yeah, no, often we are concerned about some things about the model being misspecified. So the interpretation of MLE, there is an interpretation of it. Great question. If you look back, right, what does the estimator look like? Let's look back at that. So the estimator is, maximizing this thing, right? So it's maximizing that. Okay, and so if you just think about, you can think about what it converges to if the model is misspecified. Okay. And the key thing is that under some regularity conditions, the limit of the argmax is the argmax of the limit. And one of the neat or useful things about formulating MLE like this is you know what the limit of that objective function is by the law of large numbers, right? Let me go back. That's going to converge to. So, right, let's just talk about that for a minute. If you look at 1 over n, summation over I, log f of wi, given theta, law of large numbers, right, says that that converges in probability to the expectation of log of f of wi given theta, right? And so, you know, the limit of the argmax is the argmax of the limit. In general, under you don't need any assumptions for this other than regularity conditions. There doesn't depend on the regularity conditions. It depends on identification, but it does not depend on correct specification. So what the MLE will converge to in general is this. Sorry, log in there. Okay, over the whatever set of parameters you're looking at. Okay, so there's that interpretation. You might say, so what? That's a good question. Okay, that may not or may be interpretable something. In some cases, in exponential families, you get the mean right. Okay, that if you have the mean correctly specified, that's enough. You don't need the rest of the distribution specified. But in general, you have this interpretation. This dates from Huber, and then there was a nice paper by Hal White in Econometric in 1982 about this and how to check it. But that's what you got. Now, some models, you know, you can hope to have you can hope to have some interpretation of this, and there are some models that are not exponential families where you can find some, but in general, you know, you have to work kind of hard on particular structural models, I would say. Is that fair, Nikhil? You have to work kind of hard with particular structural models to figure out what it might be if the model's misspecified.
Yeah, I'm not sure if I understood you correctly, but does that mean, say if it's from an exponential family, for example, the normal distribution, right? If just we correctly specify the mean, then it doesn't really need to be normal distribution.
Absolutely. Yeah, and that's true for other models too, like the Poisson model, for example, model of discrete data. If you get the mean right, then MLE is consistent. It's even better than that for the Poisson model. You know, conditional maximum likelihood in panel data, which, you know, conditions on and fixed effect, that's consistent without the Poisson assumption. You just have to have the mean right. So it's that one, that one's a more advanced result, but yeah, one of the more useful results in nonlinear panel data. So you have a question? You want to follow any follow-up you want to? So let's just stick with the exponential family. So like if you have just a density which has got this exponential form, which I'm not going to try and reproduce at the moment, exactly what it is. Then yeah, if you get the mean specified right, then MLE produces a consistent estimate of the mean, even if the distribution is not correct. Yeah. Yeah. Any other questions? Great question. Okay, so inference. I'm going to talk about that a little bit in just a couple minutes. So what happens, and you know, the Nikhil had in mind was, you know, this formula is not right. So like in the exponential family case, when the distribution is misspecified, this formula is not correct in general, even for the mean parameters. Okay, but you can get a formula that is correct if the estimator is easy to compute. This is not, you know, that applies to very limited class of structural models. Mostly they're quite difficult to compute, but if it's easy to compute, then there's this, you can just bootstrap it, and I'll get to that in just a few minutes. They got the right standard error. Okay, otherwise you get this simple formula here. You know, sorry, the simple consistent estimator you have here, that doesn't work, but there's a kind of a three matrix form, a sandwich. It's actually called the sandwich formula. Maybe I should do that actually. That's worth doing. Okay, so let's just go back to that. This is a sandwich formula. And what it looks like is in the middle, there's a matrix, I'm going to call it omega hat, which is the sample average of the score, outer product, sorry, WI theta hat. That's a WI theta hat prime. Okay, that's going to be in the middle. And so what it looks like is your V hat or your V tilde that will be consistent will be J hat inverse, this omega hat, J hat. And this is a sandwich formula that's a robust variance estimator. And so that would work for an exponential family where the distribution is specified, but you get the mean right. And just as you know, I mean, it's a safer thing to do for standard errors in general. Actually, you may be able to think about some possible interpretation of the parameter here, your quasi maximum likelihood parameter, as it were, the theta hat, you know, the limit of the, I'm sorry, the argmax of the expected log likelihood. You may be able to interpret that. And if you want to correct standard error, you would need to use that formula or do the bootstrap in a particular way. And I'll get to that in a minute. Okay, any other questions about that? Quick example, binary choice. Okay, we'll talk more about much more general things in a few minutes, but let's look at this. So W, the data consists of an outcome variable Y, which is binary. And you can interpret it as some Y star, which you don't observe being greater than or equal to 0. That's 1, Y is 1 if that Y star is greater than or equal to 0, and there's 0 if Y star is less than 0. Okay. And then a typical specification of this is to say that Y star is X prime theta naught minus epsilon, where epsilon's independent of X. Okay. And has some CDF H of U, probability that epsilon is less than or equal to U is H of U. In this model, this has a neat interpretation. Y star can be often interpreted, and we'll get to an explicit version of this for multinomial choice, as the difference of utilities of the choices of Y1 and Y0. For example, you know, Y might be mode of transportation, like you took the bus from the lodging, or took a bus from the lodging, or you walked today. Okay, and then X are observed characteristics of utility, like, you know, travel time, price of the bus, whoops, and income. Okay, and then the epsilon in the way that many people think about it, including me, is epsilon is unobserved heterogeneity. You have a utility. There's an unobserved heterogeneity part, a part that varies across individuals in a way you don't observe. We'll come back to this again in multinomial choice. And that's what the epsilon represents. And then if you have a distribution for epsilon, the difference of, again, we'll get to this, the difference of the observed parts of the utilities for the two parts, then you got, you know, the probability Y equals 1 given X is just H of X prime theta naught, where theta naught's the true parameter value. Probe it, you know, as most of you know, that's just where the CDF is the standard normal CDF. Logit has this form. It's this exponential form, e to the u divided by 1 plus u to the u. Okay, any questions about that? It's a standard example, but really useful. Here, this is a conditional PDF, okay? And there it is, that's the conditional PDF. So it looks like right there, it's conditioned on X. You know, to get the MLE, you just take the log of that and average over the data, and that's what that is, okay? And then maximize it, and that's not data, that's theta hat. Okay, and then this estimator is consistent asymptotically normal under what? Okay, it's under, you have the correct CDF for epsilon. Okay, Binary choice is not one of the examples where it's neither is multinomial choice, where there's consistency without the distribution being correct. In general, that's not true. If the distribution is incorrect here, it's not consistent in general. And there are some, there's some interesting things that can happen. If X is multivariate normal, it turns out it's consistent up to scale. But that's an unusual, that's, we don't really think about X ever being multivariate normal. So binary choice, even a simple model as that, the distributional assumption matters for interpretation of the parameters. And if it's not true, then we don't generally have a good interpretation of what the parameters are. Okay. All right. Any questions about that example? Simple, straightforward, hopefully. Okay, but questions are always welcome. Okay, so let's talk about GMM then for a few minutes. Okay, so generalized method of moments. It's based on not a specification for the density, but a specification of some functions that are known to have expectation 0 at the true parameter value. Okay, so that's the key assumption for GMM is you have these functions, there's an R by 1 vector of functions specified to have mean 0 at the true parameter. So the expectation of these functions, all of these functions is 0 at the true parameter. GMM is constructed so that it's what you do, right? As you know, you take the sample average of those moment functions and then say you choose theta hat. So the sample moments are close to their population counterpart of 0. Okay, and the way you measure that is you just take a positive semi-definite matrix, it's R by R, can depend on the data. You form a quadratic form in the moments, the sample moments of the moment function, you choose theta to minimize that. Arg min instead of arg max, you're just trying to set the parameters so that thing's as close to 0 as possible, right? You just want this thing here to be as close to 0 as possible, actually that, okay, right? Okay, and this, thing in the middle just measures what closeness is. If you read, who's read Lars's paper, Lars Hansen's paper, 1982, probably not very many people, right? Actually, the notation, he actually uses norm notation. That's throughout. It's a little harder to follow. It's actually a lot easier to learn GMM from the Hansen and Singleton paper. But of course, Lars's paper was terrific and been very influential. Okay, so fundamental condition for consistency and asymptotic normality of GMM is that the R by 1 vector moment functions actually has mean 0 at the true parameter. And furthermore, if the true parameter is not, the parameter is not the truth, the expectation is not 0. Okay, so that's this one, right? This one is the correct specification condition. Here, right? So that's the correct specification condition. It says that at the true parameter, the moments really are 0. And then the identification condition, so this is identification here. It says that if you change the parameter, you change the expectation of the functions away from 0. Okay, so the properties of GMM, or you can summarize those similar to maximum likelihood. It's just a little more complicated. If you like G sub theta be the derivative of the moment vector with moment function vector with respect to the parameters. So that is an R by K matrix. R by P matrix. P is the number of parameters and R is the number of moments. Okay, and then you look at its expectation of that at the true parameter, and then you also look at G hat, which is the kind of obvious thing where you substitute in the estimator and take the sample average to estimate the expectation. And then we also used psi as the probability limit of the weighting matrix. Omega is the second moment, population second moment matrix of the moment vector, and then omega hat is just a sample second moments. You know, you plug in an estimator of the parameters, you take the sample second moments, and then the asymptotic variance looks like that in general, this complicated formula. And to get a consistent estimator of it, you just plug in, you know, the G hat for the G, psi hat for psi, and omega hat for omega into the formula. And under the regularity conditions, V hat will be consistent for V. So under, you know, correct specification, identification, you get consistent, and a few other regularity conditions. Okay, you got root n GMM estimator minus the truth converges to normal 0V, and the V hat is consistent for V. Okay, so that's what we're going for. We want to do inference, right? We want the same thing as we had with maximum likelihood. We want consistent asymptotic normality and a consistent estimator of the asymptotic variance. Okay. All right. Okay, so that's the proposition again, and we can summarize that as GMM is consistent and asymptotically normal with asymptotic variance V, and V hat's a consistent estimator of the asymptotic variance. And then, you know, one of the things that's common here and began with Lars's paper and Hansen and Singleton is that there's an efficient choice of this weighting matrix. And the efficient choice is the inverse of the variance matrix of the moments that minimizes the asymptotic variance among all possible weighting matrix. And you can construct an estimator of that doesn't affect the asymptotic variance of the efficient weighting matrix by just taking the sample second moments of the moment functions and then using that for your weighting matrix. Okay, so that leads to the common important two-step GMM, right? And the two-step GMM consists of, in the first step, you get some initial estimator, right? You form this, your initial estimator here is theta tilde. So theta tilde is some initial GMM estimator. For, you know, some known C hat, you form that, and then you invert it. You form that second moment matrix, you invert it, you plug it in, you do GMM a second time, okay, and you get a new theta hat with this as its weighting matrix in the middle, and that's known to be efficient in the class of GMM estimators for the given moments. In other words, right, if you, you know, that's the one that minimizes the asymptotic variance, okay? One feature of this that, you know, is now pretty widely known is this estimator, this two-step GMM estimator, is actually quite biased if you have a lot of moments and not very many parameters. So if there's a lot of over-identifying restrictions, you know, this thing can be biased, and that's particularly true when you have instrumental variable settings. When you've got the moments consisting of, like we'll look at in just a second, you know, you've got a residual or many residuals, and you're multiplying by instruments. Using a lot more instrumental variables than you have parameters, this two-step GMM estimator is biased in general. Right, that's I can talk about it more a little bit later. What do you do about that? Well, there are alternatives. If Josh Ingris were here, he'd say do liminal with linear instrumental variables. That's a good suggestion. And there's other more complicated things that you can do. There's something called empirical likelihood, continuous updating, which fixes this problem, we're not going to talk about this. I mean, those things are really hard to do for large structural models. So the main thing to get out of this is just a warning. You know, if you're pushing the number of moments out, why would you do that? I'll come to that in a minute, but the reason you would do it is it's like that can increase efficiency, and maybe your initial GMM estimator had a pretty low or pretty high asymptotic variance, and maybe your coefficient's not significant, even the one you're interested in. So maybe, hey, let's add some more moments to do it. It's fine if they're valid, you can do that, right? You have to just be really, really sure that they're valid, of course, before you do that. Because if you add moments, right, they're invalid, then you break the correct specification, and general GMM is not consistent. Okay, so they have to be valid. You just can't go looking for instruments anywhere. Well, we'll come back to that in a couple of minutes, actually. Why don't we talk about that a little bit? Okay. But, you know, as you do that, you're also building bias into your estimate. Okay, and, you know, that's an important thing to think about. Very famous examples of this where there's some evidence that there is some bias, but, you know, not really accounted for in the initial good, excellent structural papers. So, okay, just a warning about that. Okay, so an example, any questions, okay, about GMM? Yes.
Are there any gains to running the two-step GMM a third time? So you estimate, you get data with some, yeah.
Yeah, great question. So there can be some in some settings, but there's no general proposition about that. Yeah, that if you just, so you're suggesting you want to do the two-step thing, you know, but iterate on this weighting matrix. So you would get, you're saying you got a two-step efficient GMM estimator, then you take that efficient GMM estimator, plug it back in, and then you recompute the high efficient weighting matrix and get a new GMM estimator. As far as we know, there's no really good theoretical reason to do that. What does work, and the continuous updating estimator, that actually reduces bias. Okay, so let me talk about that. So for that one, what you're doing is you're not iterating like that. Instead, you're simultaneously minimizing over the theta in the weighting matrix and the theta on the outside. Okay, so let me just talk about that for a minute. Okay, so so I'll just say what that is. If you take omega hat of theta to be equal to this, and actually one of the things that there's some evidence that's a little better, and I should probably mention this actually, is I'm going to give you the thing that's a little better. I'll give you the thing that's a little better here. We think, go away. Okay, one of the things that's a little better, we think, is to use this as the weighting matrix. Some evidence that it's better for certain tests. We'll do what we did before, I equals 1 to n, g of wi theta, g of wi theta, and then we'll actually subtract the mean off that. Okay, so minus g hat of theta. Yeah, there's some evidence that the behavior of this is a little better for certain tests. The continuous updating estimator that looks like theta hat is the argmin of the theta, and what you do with that is you minimize simultaneously over theta in the weighting matrix, and I need an inverse. So inverse, sorry. That, if you erase that, sorry. This is one I should try. Universe. And minimize over that. Okay. So, well, you might say, well, why don't we just do that? It turns out this objective function is pretty hard to minimize. It's very flat over in IV settings. It can be very flat. And so finding the minimum is a lot of work. And since you're doing a structural model, and you maybe it's hard enough to compute the moments, right? And do GMM over like a fixed weighting matrix. And boy, you want to put theta in. And minimize over theta in the weighting matrix too. So it's hard to compute actually. And so that's why it's not done much. Plus it's got, it's hard to compute. Plus it's got this property that it tends to have a much flatter objective function. So it's harder to find the minimum. But it does get, it does lower this bias problem. I'm sorry, that should be right. Yeah, but it does help with the bias problem. So that one helps. Now, what's the intuition? Why does that one help and not the other one? It's because when you're minimizing over this, if you think about the first order condition, there's another term there, which is the derivative with respect to the theta in the weighting matrix, right? So the first order condition before, you would, sorry, I was going to cover it. I'm not trying to do that, but the first order condition before, without the theta in the middle, you're just going to take the derivative of the g on the outside, right? And that'll be the derivative, and that'll give you your first order condition. When you minimize over the one in the middle, there's another derivative that shows up, and it turns out it takes out the bias. The first order, it takes out the bias out of it. So, okay. So that's useful to know, but I think in structural modeling, it's kind of hard, really quite hard to do actually. So, and even in IV settings. Okay, so the reference on this is a Hansen, Heaton, and Yaron. It's the kind of the that is Hansen, Heaton, and Yaron. Sorry, Yaron. And I'll have to look up the exact reference. It's, yeah, I don't know. So I don't have it on the top of my head, but I can, I'll get the exact reference for later. Okay. And then there's been other work since then, so that you can read about it there. It's less biased than the Monte Carlo, and then you can show theoretically that it's less biased for sure. Okay. Any other questions about this? Yes.
Sorry if this is such a basic question, but you can have an estimated bias, but asymptotic normality and consistency can still go through, right?
Yes, it does. That's true. And yes, it does. But what this means is that because it's biased, the confidence intervals tend to be shifted. And that's a bad thing for coverage probabilities. If you want a good probability, a confidence interval that's accurate, and then you get bias, it shifts it over. And if you start shifting it too far, you're not going to get a 5% test, or what you're going to get like a, what would it be? Is it shifted too far? You might have like, a lot of rejections. It tends to increase the rejection probability above the nominal value when you get bias like that.
Can you try to correct them, like in terms of how you do them?
You can, yeah, there's multiple ways to do it. You can, yeah, so good question. What would you do to correct it? This is one way to do it, continuous updating, right? And this is actually, you can look at the efficiency properties of this, and it's pretty good in the IV settings, actually. Limmel, like it, so, you know what limmel is? Maybe I didn't tell you, but anyway, there's this thing called limited information maximum likelihood for linear IV. And it's in most of the programs that you can do. That's actually an efficient way to do the bias correction in that setting, and almost stochastic case, right? But in other settings, in the general GMM setting, there are some good efficiency properties of this too. So, yeah, but that's the problem. So that comes up other places, can come from nonlinearity. And other things too. And there's But why don't I talk a little bit about how to do bias corrections if you want to do it to try and correct this. We'll do that we can do that when we talk about the bootstrap. Okay. Any other questions about this?
There's a question in the chat. How many are there any standard guides on how many and which modes to choose?
Oh, good question. There are. Yes, so there's some work on which moment restrictions to use. If you want to choose among a set of them, there's some papers on that. Stephen Donald and I have a Journal of Econometrics paper, and and for linear IV, we have an econometrica paper that talks about among different groups of instruments how to choose. So you can base it on the data. If you're interested in, and if you're interested in asymptotic efficiency, so know your moments are right, the moments you have are right, and in structural models, that would generally be the case. What you're doing is the only thing you're going to put in is things that your model tells you are correct moment conditions, right? Some other branches of applied econometrics, you might, or not branches, but other places where people do applied econometrics, they're not that sophisticated about thinking about where the instruments come from necessarily. So anyway, so you might worry about that. But then it just comes down to efficiency issues. In these other places, people, you can think about, in fact, I know this happens in structural estimation, right? You can think about trying to select among moment conditions, which ones, and try and use select among moment conditions according to which are valid. And there's a paper by Don Andrews. Do you remember what the year was?
2001.
2001 paper by Don Andrews and Lou. Yeah, there's an excellent Journal of Econometrics, and Don had a paper in Econometrica before that one. 2001 Journal of Econometrics.
That was the moment and model selection paper.
Yeah, okay.
And then there's a prior one.
Okay, so let's just refer to that one.
Prior one is 2000.
Yeah, okay, so let's see. So Andrews and Lou. And it's 2001.
That one is 2001, and the previous one is a couple years before that. I'll look that up.
So they talk about moment selection, which, and basically you take the GMM objective function, you add a penalty for the number of parameters in a way that's known how to do in other settings, and then you select which moments minimize the GMM objective function plus the penalty. Okay.
Same office in 1999.
In 1999. Okay. And that's Econometrica?
That is
Okay.
Econometrica. Andrews in 1999.
Okay.
There's another related question, which is, suppose you have many moments that you could theoretically put in. There's a function of them that the structural model doesn't tell you which function to put in. Right?
Yeah.
So is there a way to select the best function of the moment? Maybe two is the more recent versions of that.
Yeah, so you're pretty sure they're all right? Is this the case that they're all right?
Yeah.
Okay, if you're sure they're all right, yes, there is a way, but it's kind of, I don't know that's in the literature actually. So this paper Stephen Donald and I have is probably the closest that comes to it. It's selecting instruments and with conditional moment restrictions. And it's in the Journal of Econometrics. I don't know the year. I can get the reference for it. Yeah. Yeah. For that, yeah, no, there is what you do actually. The thing that works if you know the instruments are right that you're selecting among, you want to take account of this many instrument bias along with the variance. And what you do is you take an estimate of the variance and you add to it the squared bias. That's basically what the selection is, and that actually works. That actually works. So
Which year is that?
what?
Which year that you take it?
Why don't I have to go look it up. I don't remember. Some of the papers that I've done, I remember. Not that one, sorry. Okay, great questions. Any other questions? Yes,
Like this penalty term idea,
yes.
it's not quite the same as a rich regression, but kind of the same intuition about you try to, for complexity, you wanna,
Yes, yes, absolutely. It is a similar idea. You're trying to control complexity of the model in choosing it. Right, because if you just use the objective function, you are trying to do that, but there's a pretty good, fairly straightforward intuition for it. You're just trying to use the objective function. You kind of put in more moments, you're going to make it get bigger. And so or put in more parameters. Sorry, that's not the right one. Put in more parameters, you're going to make it get smaller, right? Because you make it more flexible what you're minimizing over. So the objective function is getting smaller. So you need a penalty to kind of control for that in the selection. Yeah. So that's what. Yeah. Good question. Other questions about this? Okay. Oops. Okay. So I sort of said this, but comparing MLE and GMM, so that's where we are. The first order conditions for MLE make it a special case of GMM, right? The MLE first order conditions are that the sample moments are 0, where the moment functions are the score, the derivative of the log likelihood for an observation with respect to theta. You never want to do that if you're doing maximum likelihood. You never want to just find the solution to first order conditions if you're doing maximum likelihood in a structural or other complicated model, because you may have multiple solutions to the first order conditions in those models, so you always want to maximize the likelihood. Okay, but it is true that it is a special case of GMM, and they're actually the optimal moment functions. You can think about one form of the maximum likelihood efficiency result as these are the best moment functions. Using those moment functions gives a GMM asymptotic variance that's smaller than any other GMM estimator. Okay. Right, and GMM, if there are number of moments equal to number of parameters, you can show asymptotically it's the same as just setting the moments to 0. Okay, for GMM, maximum likelihood GMM, just want to emphasize it's, you really should check the identification. Okay, you really should have good reasons to think that these parameters are identified, because otherwise, you're not going to be able to tell from the data whether. I'm sure that everybody does structural estimations and probably has a lot to say about that, much more informative than I do, and you'll hear more. But it's important to know the parameters are identified, right? Maybe you can tell this from the standard errors. The standard errors are really big. Maybe that's evidence that it's not very well identified, and it is. But the formal link between those two things is not completely clear. Anyway, so it's just important. Identification is necessary. Soapbox statement, identification is necessary to be able to determine from the data what the value of the parameter is. And it's difficult in structural models, and other people in this room are going to have a lot more to say about it probably, but you could check a local condition. A condition for local identification is the derivative of g hat with respect to theta is r. You take the derivative of the moment function with respect to theta, you plug in theta hat, some different thetas, and you can check whether it looks like, it's R or something less. R is the number of parameters. In some sense, the standard error formula already does that. Okay, so getting a large standard errors is an indication that could be a problem. Of course, it's essential. You must have more moments than parameters, and you say obvious. Turns out in that some places in empirical work, I won't say anymore, I should say anymore. Anyway, it's like this condition comes up and not satisfied. Okay, so anyway. Okay, so let's just talk about this, just for, talk about MLE and GMM. Okay, so let me ask a few questions. Which of, and feel free, these are non-rhetorical questions, otherwise, feel free to answer them. Which of MLE and GMM estimator uses the most information about the data distribution? Start with an obvious one. So which one uses the most information about the data distribution? Go ahead, which one? Yeah, which one uses the most information about the data distribution? Mind if I call you?
Yeah, I would assume it was an MLE because we need to correct this, like.
Totally, yeah, you're assuming completely what the distribution is. So it uses the most information about the data distribution. And so one kind of, the thing that goes with that is which estimator is consistent under weaker restrictions than the other. So the MLE, you need the, in general, you need the distribution to be correct. For GMM, what do you need? It's need the moments to be correct, right? So GMM consistent under weaker restriction. Should one always use the most efficient estimator? Should one always use the most efficient estimator? That's a pretty open-ended question. Should one always use the most efficient estimator? Anybody want to share a view? So here's an example. So I'm working on this problem, and this is Nikhil already brought this up, but and I can get some more moment conditions and add them. Should I do that?
It depends on the bias.
Okay, great. Depends on the bias. Right. Yes, absolutely. Yep. So not necessarily. Right. What's the trade-off between efficiency and robustness for these two types of estimators? Right. So what do I mean by that? It's like, so this is present in all of the econometrics, basically. Sure, you can get like a more efficient estimator by using more information. But there's something that goes with that, which is if the information you use is incorrect, it's biased. Okay, so looking at, do I want to go for a more efficient estimator? What if my standard errors, they're big? What am I going to do? And yeah, look for more efficient estimator, but the thing you should always be aware of, yeah, but that comes at a cost, which is it could be misspecified, the information you're using, and so that could be a problem. And a great way to test for that is a Houseman test, right? You compare the efficient estimator with something that's not efficient, and that's a great way to test for that. Use a formal test. Okay. What's the trade-off between, we talked about this, between efficiency and robustness from increasing the number of moment functions in GMM? What other reasons are there to use maximum likelihood or to use GMM? What other reasons are there? Structural estimation? What other reasons?
The likelihood can be intractable.
Absolutely. Yep, the likelihood can be intractable. Yep, absolutely. There may be lots of unobserved variables you have to integrate over to get the likelihood. Yeah, and so that can be intractable. Great. Thanks. Any other thoughts on this? Okay, so these are just some of the questions to think about. So one of the things about doing MLE, they're both important, and GMM, they're both important in structural estimation. Sometimes you have a choice between them too, and it's good to think. These are some of the things to think about when you think about the choice. Any questions? All right, let's talk inference for a few minutes. So we said, right, that with the statement of these results, that the thing you're going for is asymptotic normality and the consistent estimator of the asymptotic variance. So those, once you've done those two things, what that gives you is the ability to do inference. You can, form asymptotic t-tests, and you can also test actually, a multivariate hypothesis about the parameter vector. Okay, so this is kind of, what you're going for when you're looking to show that you can use some estimator for inference. Theta hat consistent asymptotically normal, B hat's a consistent estimator of the asymptotic variance. The standard way to conduct inference then is to treat theta hat as if it was normal theta naught and with variance B hat over N. So if you do everything based on that, you're right. That doesn't describe the asymptotics the right way. You got to do root n theta hat minus theta naught conversion distribution of normal 0 V. That's the correct way to do the asymptotics, and B hat's consistent for V. But this works perfectly fine to describe what you do. And so based on that, you would take theta hat J plus or minus the critical value for the normal times this asymptotic standard error, which is B hat JJ divided by N. Z of 1 minus alpha over 2 is 1 minus alpha quantile of the standard normal 0, 1. So this is just the standard T confidence interval. And then you can also test a vector of vector of hypotheses about the parameter vector theta. You can test the null hypothesis that h of theta naught is equal to 0 for an S by 1 vector of functions h of theta using the Wald test. And this is simplest to, again, in this context where you just have an asymptotic, consistent estimate of the asymptotic variance is the simplest one to talk about, right? And the h hat here is what that is a derivative of h with respect to theta evaluated with theta hat. Okay. And then you would reject if this test statistic, you reject the null if this test statistic is greater than or equal to the critical value for chi-squared with s degrees of freedom, where s is the number of hypotheses that you're testing, or the dimension of the hypothesis you're testing. So all you need, is a consistent estimator, is a consistent asymptotic normal estimator of theta naught and a consistent estimator of the asymptotic variance. Okay. So like when you're writing the econometrics paper, you want to say those things in the conclusion. Anyway, so that's what you need. Okay, so that's great. Okay, how does that work? Well, not always so great, actually, because the standard errors might not be so good. Maybe you're using the maximum likelihood ones, and they're not right if you unless the likelihood is correctly specified. And so there's other things you can do as well. The other thing is, in structural models or in lots of econometric models, it can be hard to compute these standard errors potentially. You get into issues where you're doing two-step estimation. You're going to estimate some parameters and then plug them in and do estimation, and that makes the formulas a lot more complicated. Bootstrap is a way to avoid that, and also a way to get robust standard errors. Okay, so let's talk about that for a minute. Okay, so so in structural models, these things can be difficult to compute, and in the limited cases where the estimator is not so difficult to compute, and there are some, two-step estimators. There are some simple two-step estimators that have that form. You have some regressors that you have to estimate somewhere else, and you want to go plug them in and do least squares. That's a pretty simple estimator, and the formula for the asymptotic variance is very complicated, so you can skip that. and you can just do Bootstrap to do that, okay? And you also, in some cases, VHAT may be difficult to compute. Okay, you also may want to allow for some aspects of the likelihood or some moment functions to be possibly misspecified, but not compute the sandwich variance estimator. You may, even in GMM, you may want to let there be misspecification, and if it's over-identified, the standard errors are really complicated, actually, because now the moment functions aren't satisfied at the limit of the estimator, and so you get two additional terms, one involving the weighting matrix and what its limiting distribution is, and another involving the derivative of the moments and what its limiting distribution is. And you never want to compute that analytically. And you don't have to. If you can bootstrap it, it gives you that. Okay, the bootstrap will give you that. Okay, so that's the other nice thing about the bootstrap. It avoids complicated formulas. And it also, in general, works to get standard errors when the model is misspecified. Okay, as we talked about, you may have cases where you can interpret the parameters you have, even though your model is misspecified, and the bootstrap produces standard errors that work when the model is misspecified. Okay, so the bootstrap that we're going to talk about here is the non-parametric bootstrap. So you draw. I'm just going to describe the algorithm the way this, that's the way the bootstrap's usually described. You describe the algorithm. The algorithm is, you draw n observations at random with replacement from the data. Okay, and you index those by b. So b is an integer. B, ranges from 1 up to b, where b is the number of bootstrap replications. For each time you draw the data, you compute the estimator, okay? And you just, you apply the same formula that you applied, including all the steps to compute from the simulated data, you compute the estimator theta hat. So for example, a good example of this is GMM. That's really by far the most common two-step estimator in use. Multi-step estimator use in econometrics. The first step is the weighting matrix, right? However you're going to estimate, the first step is the weighting matrix. So you got that, and then you get your moments from the simulated data, and then you minimize the objective function on the simulated data or your bootstrap data. Okay, and that's a two-step estimator. You're estimating the weighting matrix in the first step. And you're doing then in the second step, you're minimizing the quadratic form of the moments. And then what you do is you repeat that b times. And you can just take the standard errors of that to get to do inference. You can use those standard errors, the sample over the bootstrap sample, the sample standard deviation over that. And that is a correct standard error for the bootstrap, or you can use a confidence interval based on the distribution of that theta hat minus theta naught being approximated by the distribution of theta hat bootstrap minus theta hat. And the bootstrap percentile confidence interval looks like this. It has kind of a funny form, but this is better than just doing a percentile confidence interval in small samples. So. Okay, so the nice thing about it, so like if you want GMM standard errors that allow for misspecification, do this. Don't, there's like I said, there's a complicated formula, but this is just by far the simplest way to do it. Yeah. Okay, what does it depend on? Depends on the ability to recompute the estimator, right? And in structural models, that may not be so easy. So it may not be that. I don't know. There are people in this room who have a much better sense of that than I do. Let me ask you, bootstrapping for structural models? That's the answer. So maybe not.
No, we don't do Bayesian, like Markov, chain Markov. Now, there are some examples. The guy Andre Noritz, they do that, dynamic discrete choice with serially correlated errors, and they can use this Markov chain Monte Carlo and solve the DP going along. So it's not always true, but in many cases.
So that's one example. The other thing that some people do is, I don't know if this is right or wrong, you should tell me, is bootstrap the moments.
Yes,
Data hat, and then use the delta method to get the,
yeah, that's fine. Yeah, and that's good.
that's
'cause-
easy, that's not that hard.
Yeah, okay, so that's good. It doesn't have this, it's not robust in the specification, but yeah, that's great. Yeah, that's great. Bootstrap the moments and then use the,
Add data hat,
yeah,
and then use delta method.
yeah,
Whitney?
yes,
I think it depends on the estimation method. So if you're using CCP estimation, bootstrapping is, I won't say common, but quite feasible because the estimator is least squares. And so then it's straightforward, but there's the least squares in the sense that you're taking this prior stuff and then using the plugins that you're talking about. And I think that would actually be an ideal situation where you would use the bootstrap, because computing and analytically, you're worrying about the first order conditions and all the things that you're sort of implicitly referring to, whereas a bootstrap doesn't do that. And so it would be a practical alternative.
yeah, very cool. So conditional choice probabilities, that's the next one you're gonna talk about in a little bit, right? And that's the multi-step method, right? Where the
Yes.
bootstrap's nice.
Yes.
I guess one more thing you could do is classical and CMC stuff that will allow you to correct, this is sort of building on John's comment.
Yeah,
Will correctly give you the distribution of the estimator as well as the quotient.
cool. Yeah, absolutely. That's a good thing to do. Thank you. Great comments. Any questions about any of that? So, yes,
What's the first thing that Phil said about how to use it, to bootstrap the moments, and then what do you do?
yes. Okay, so let's see. Let's try this out, see if we can talk about that. Okay, so you have in mind, let's see, how would you think about this? So you would think about this, the way that I think you're thinking about this is you bootstrap the moments, you drop in the moments, right? And then you woke and do the delta method. I see. So I'm thinking, the way that I'm thinking you would do that is if you have, do you mean the moments, you mean G hat?
Yeah.
Okay, let's look at that actually. So
I can find the reference.
yeah, it's actually in, yeah, if you actually, where you can find this, if I'll talk about it, but you can find a reference, I think on the open courseware, Victor Chernznikov's 14382. It's there actually, but we can talk about it briefly. It's like, the theta hat, let's just do theta hat is kind of approximately, sorry, theta hat minus theta naught. It's kind of approximately, in the asymptotics, kind of looks like G hat prime. Oops. C hat, G hat, inverse G hat, inverse, sorry. I'll come back, do this start over. Yeah, so G hat. Minus theta naught. G hat. C hat, G hat, inverse. G hat, C hat, and then you got this. So that's what the asymptotics tells you, that it's approximately equal to this. And so you can, if you bootstrap, if you bootstrap this part over here, right, you can bootstrap this part over here. Oops, okay, sorry. Okay, thank you. So the idea would be to so the idea would be to kind of redraw from the moments and recompute that average. And then, look at this, use this formula to get the theta hat. It's a kind of delta method, like Nikhil was saying. And so you can compute this once and then just read off in the moments a bunch of times and then recompute this. And that will give the correct distribution, but this requires correct specification. Yeah. Other questions? Okay. Okay, so what are the warnings about the bootstrap? Well, one warning, which is anecdotal stories told by a co-author. Anyway, one warning is that neither the bootstrap nor standard asymptotics is correct if estimation imposes inequality restrictions on some of the parameters. Yeah, so anyway, this comes up. For example, some structural models have many probabilities possibly for something unobserved that's happening, some discrete unobserved thing that's happening. And you certainly want to constrain probabilities to be between 0 and 1. So you might think initially, oh, I can just bootstrap that. You can't actually. It gives the incorrect standard errors, incorrect distribution. Okay, and so that's one place where the simple bootstrapping we're talking about fails, and that does come up sometimes in structural models. And we'll talk about why. Well, we can talk now about why that is. There's a discontinuity in the limiting distribution when the parameter hits the boundary. Okay, and what happens is when you hit the boundary, the parameter changes from being normal, okay, in the limit to being a half normal. It's actually a censored normal. So half probability it's at 0, or some, it's more complicated than let's just take the sample mean. You want to estimate a mean subject to the constraint that it's actually I use up the whole thing. So let's just talk about this for a second in the context of, suppose you want to impose the restriction on a mean that it's greater than or equal to 0. The natural thing to do is just say, take theta hat to be, the max of x bar and 0, right? 0. Okay, that imposes a restriction that the mean is greater or equal to 0. Great estimator, it's a fine estimator. Its limiting distribution when the true mean is positive looks like this. Limiting distribution. It's the usual standard normal. This is mu greater than 0. So that would be a root n. Theta hat minus theta naught. And what it looks like when you hit 0 is it looks like this. Okay, so when you hit 0, you're going to spike at 0 of a half, and then this is right at 0. And then you get a normal above it. So this is a spike. Problem with that is the limiting distribution is discontinuous. When you hit the constraint satisfied, all of a sudden the distribution shifts. And what the bootstrap is doing is it's using the distribution of the data that you have to approximate the true distribution of the data. And if that approximation is discontinuous, at the truth, you have a problem, right? Because your data, your data is what it is. And it is true that the distribution of your data is approaching the distribution of a single observation. The empirical distribution of data is approaching the distribution of a single observation. That's fine. But then if that in the limit that's discontinuous, when you hit that boundary point, then the bootstrap doesn't work because the approximation isn't continuous. Okay, so bootstrap fails. Okay, so yeah, but I'm not gonna say. Never mind. Never mind. So I want to talk a little bit about a bootstrap method that does work in this setting, and this is from a recent paper. So this is kind of the newest thing in these two lectures. And I'll talk about it for just about 9 minutes before we break, and then we'll come back to it. Okay, so we're going to focus on, the point of this is there is a fairly straightforward bootstrap procedure you can use to get the correct critical value for a test with inequality restrictions. Now, it's simplest in the case of linear IV, so I'm going to focus on that case, and I'll indicate, what gets more complicated in nonlinear models and in partially identified models as well. But I'm just going to do the simplest case, okay, for exposition purposes. Okay, so focus on linear IV estimation with equality and inequality restrictions. So the model is just linear instrumental variable models. Yi is Zi prime theta naught plus epsilon I. And there's some instrumental variables, that's the X, those are the IVs. Instrumental variables, the X, and they're orthogonal to the epsilon. And again, the data are IID. And want to describe a test of a null hypothesis of this form. Okay, you got some equality restrictions and some inequality restrictions. Okay, and then the way you get confidence intervals here is by inverting the test statistic. Okay, and we'll base the test on the two-step GMM estimator with optimal weighting matrix. Okay, so need a weighting matrix, an estimate of weighting matrix. So using an initial IV estimator, theta naught, and omega hat, a corresponding estimator of the second moment matrix of the moments. Okay, and so, right, so there it is. There's our omega hat. Okay, there's the residuals. Okay, that goes into the omega hat. That's the way they're defined there. That's just the weighting matrix for linear, optimal weighting matrix for linear IV with possibly heteroscedasticity. Okay, and then the moment functions look like this, right? Those are just the sample moments of products of instrumental variables and residuals. Turns out, for fairly deep reasons that lead to weaker regularity conditions, so it's easier to work here with the square root of the GMM objective function and doing a test. And so take Q hat of theta to be just the GMM objective function, take its square root and multiply by root n. Okay, so the restricted GMM estimator would be this, right? You minimize the subjective function subject to the equality restrictions, no problem. Oftentimes that's done by just substituting those out. And then plus the inequality restrictions. So in this case, this is a square root of a quadratic objective function, and you're minimizing subject to inequality constraints. And that's quite an easy thing to do computationally. There's programs that'll you can plug and play and do that. Okay, and then you have the unrestricted. And then the test statistic is just the difference of the unrestricted and restricted objective function. Okay. The thing is, though, now you've imposed these inequality restrictions. And so you could talk about bootstrapping that, but it doesn't work. Okay, that doesn't work. And so what we do is we bootstrap this and conservatively impose the restrictions. And what that does, so we're going to bootstrap this test statistic to get a critical value. So we'll look at a distribution for this test statistic using a bootstrap, but then we conservatively impose the restrictions in a uniform sense. It's conservative. Turns out not to be conservative point-wise, but anyway, we conservatively impose them. And what that does for you is it kind of makes this, it pushes this restricted estimate up. This restricted objective function here, what it does, what this bootstrap does is it increases this thing. Sorry. not coming through, but anyway, it increases the restricted objective function, okay? Now the first term in that T. Okay, and what that does for you is it, you know, it allows you to get a critical value that's right, okay, but possibly a little conservative. Okay, so how do you do that? Well, the bootstrap uses what's called the multiplier bootstrap. You're going to take standard normals and multiply by moments, multiply the actual empirical moments, which you've made have sample mean 0 by subtracting off the sample mean of the moments. And you multiply those by a standard normal. Okay. And then the key thing is that you're going to bootstrap this. So you're going to do different bootstrap draws. These are going to be the like the population moments, these G hats. And then you're going to conservatively impose the constraints. And the way you do that is you take the parameter set to be this. Delta represents a deviation of theta hat from theta naught, root n times theta hat minus theta naught. And then these are the constraints. And then what this does is conservatively imposes them. This Rn thing is greater than 0. And what happens, you can see here, it's a funny looking thing. You kind of have to, it's a kind of a pain to kind of think about this, but as Rn goes up here, right, then this part becomes negative. As Rn, think about driving Rn to infinity. These would all be negative, the second one. So that what you get on this right side is 0. And when you get 0, you're imposing the constraint. Okay, when you get 0, you're imposing the constraint. Otherwise, yeah, you're imposing a constraint here when you get 0. That's the constraint, the local constraint. So you're imposing it. And when by setting Rn equals to infinity, you impose all the constraints. If you set Rn equals 0, then this has some slackness in it. When the constraints, you know, this is the constraint for the actual constraint estimator, right? And that need not, that's always less than or equal to 0. So that's always positive, this part here. That's always positive and non-negative. Okay, and so that builds in, you know, otherwise, if Rn 0, all you're getting is this. Okay, and that if it's not 0, then you're not imposing the constraint. The problem is, you know, this boundary thing and what doing this Rn. So the conditions Rn goes to 0 slower than here 1 over root n. And that takes care of the problem. Okay, that takes care of the continuity problem. Okay, and I'll talk more about this, you know, in the next lecture. We'll sort of start with this. And this allows you then, okay, just to conclude, what do? You just bootstrap this. You take G hat, that's the sample, you know, derivatives. And you just bootstrap it. You put in delta as if it were theta hat minus theta naught, and then you just recompute this objective function, this test statistic many times, you know, for different deltas. And again, because this is a fairly straightforward thing to solve, this is a fairly straightforward critical value to get. And it allows you to then get correct critical values when you have an equality restriction. Okay, so come back and talk about we'll talk a little bit more about this in example, and then we'll go on to method of simulated moments and discrete time. Okay.